Hello everyone. Today we are going to discuss about the two-pass assembler for conversion of an assembly language program into the machine object code. So let's proceed. So this is the general design procedure for two-pass assembler. The first step is to specify the problem. First we specify the problem for what we are developing the assembly language program, and how do we have to convert that into the machine level or low level program. Then second one, we specify the various data structures that are used by the two-pass assembler that are used during the conversion process of the assembly language program into machine language code. Then we define the format of data structures that are used. That means the various data we use, what is the actual format of these data structures, what data does they store. Then we'll specify the algorithm that is used to convert the assembly language program into low level program. Then we look for modularity. Modularity means that we check the source program, assembly language program, that can be divided into sub parts, sub modules, so that the processing can be easy in the program, and this whole process is repeated throughout the conversion process by the two pass assembler. So the first step, that is specifying the problem, defines the symbols and the literals. Then we determine the length of machine instruction. Then we keep track of location counter. Then we remember the values of symbols by storing them in STSTU data structure. Then we process some pseudo operation codes, some operations that are defined in the program. Then we remember the literals. That means we store the literals in a separate data structure. Second one is to specify the problem. In this, we generate the object program, look up values of symbol tables into through the stigate function. Then we generate the instructions through MOT gate instructions. MOT is the data structure, machine operation code table, and then we generate the data for various commands that we use, for example ds, dc, and literals. Then we process the pseudo operation codes that are defined in the program through the POT get function. Process pseudo opcode table get function. And data structures. The first one that it use is the various databases. The first one, it inputs the source program. Then location counter is used to keep track of each instruction's address, at where the actual instruction is stored and from where to fetch it. Then machine operation table MOT, which contains a field, opcode, mnemonic, that specify the operation, then its class and its other information like its length and instruction set, whatever is there. Then another database is pseudo operation table POT, which contains a field, mnemonic, opcode, its class and mnemonic information, routine number, for example. Then a symbol table ST or SYMTAB to store each label and its value. Then we use a literal table to store each literal or variable and its location where it is stored in the memory. Then a literal pool table where all the literals are stored and used, a centralized location. Then a copy of input to be used later by the pass-through assembler. Then a copy of the data that is provided to various pseudo operation codes into the program. we hold them for the pass 2 of the assembler. So this is the structure of a mnemonic operation code table OPT, which holds the mnemonic opcode, its class, and its other information. For example, start of opcode, its class is AD, and the mnemonic information is R-1, just like this. Then comes machine opcode table. It contains, as we have discussed, a field mnemonic opcode, its class, and mnemonic information. For example, information code of IS and its length. So this is the, for example, mover is the mnemonic code, its class is IS, and mnemonic information is that means information code is 04 and its length is 1, and so on. Then comes pseudo operation table POT, which contains the field's mnemonic opcode, class, and its mnemonic information. For example, start opcode, then the class, then the class is AD, and then information is, for example, routine number we are defining here, that is routine number 1, and so on. Then symbol table, which contains the index number, symbol that is used in the program, then its address location where it is stored, and then length of the uh, symbol that is stored. So in this you can see some addresses can be determined directly, that means the address of the first instruction in the program, our other must be inferred. That means if we want to identify the address directly, the first instruction is to be stored in the table, and then we can provide references from that address for the other subsequent instructions that are stored in symbol table or the symbols. So to find addresses of other symbols, we must fix the addresses of all program elements preceding it. That means we have to fix the addresses. That means addresses can't change once you fixed, because you are referring from the initial instruction step address. From that you are referencing the other symbols. So you have to have the fixed addresses for the consequent for the subsequent symbols in the table, and this function is called memory allocation. Then a literal table, LITTAB, which contains the index number, literal, and its address location where it is stored. So the first pass uses the literal table to collect all literals used in a program. That means this symbol will be having entries through the assembler's pass 1, which will collect all the literals from the program. Pool table, POOLTAB. This contains only the literal numbers that are available in the program that we are using. So awareness of different literal pools is maintained using the auxiliary table. This table contains literal number only of the starting literal of each literal pool. At any stage, the current literal pool is the last pool in the literal table. On encountering an literal org statement or the AND statement, the literals in the current pool are allocated addresses starting with the current value in LC, and then LC location counter value is incremented with the next value in the pool table. Then step 2 is the data structure that we are using, which is used by pass 2 of the assembler. So it uses the copy of source program input to pass 1, then location counter, then MOT machine opcode table, then process opcode table, then symbol table, which is prepared by pass1. Then base table, which indicates using registers in the program, that which registers are currently specified using pseudo opcode and what are their contents. Literal table prepared by pass1 and it is used in the pass2. Then format of the data structures in pass2. Uh, First one is intermediate code. The intermediate code consists of a set of IC units, each unit consisting of the following three fields. First one is the address, second is the representation of the mnemonic opcode that is used in the program. Third one is the representation of operands, the data on which the operation is to be performed. Intermediate code can be in variant 1 or variant 2 form. This is the format of data structure passed to machine instruction format. This is the machine instruction format that is converted from the assembly language program into the low level language. So the low level form machine instruction will be having a format of first digit will be signed, then two digits for the opcode, then one digit for the operand, and then three digits for the memory operands. Then we having a look of the pass one of assembler chart, assemblers. Its flow chart that depicts the uh, graphical representation of the functioning of pass one. So this is the flowchart for pass one of the assembler, in which first we initialize, then we read the instructions in the uh, assembly language program, then we check for the labels. If labels are there, then store them in the symbol table with location counter value, and if not, then we search the pseudo code tables. If some label is there, so we will store the name ststo and data structure, and with the location counters value getting increased with every label stored in the data structure. Then we search for the pseudo operation code, that is process of code table entry for by using the POTG get function, and then we store the values. Then if found, then we determine the type of it. If the type is not defined, then we drop it and again back to the read uh, step of the flowchart. And if it is found, then we go to the pass 2, and if then we determine the length of data space required. If we determine the type, then we determine the length of the data space required, that how much space is required for the particular pseudo code operation code, and then we update the location counter value. After searching for the pseudo operation code, we search for the machine operation code, MOT, using the MOT get function. Then we get the length of the instruction. After that, we process the literals in the literal table, and then we update the location counter value. And then we again go to the read, where we read the next instruction, and so on. This process continues, and whatever we the pseudo operation codes we found, we just find their type, and then we go to the pass 2 when all the uh, pseudo operation codes are determined, all the machine opcodes are determined, all the literals are determined, all the symbol tables symbol labels have been stored in the symbol table. After that, we go to the uh, when we encounter the end statement, we go to step 2, यानी कि pass 2 of the assembler. So let's have a look at the pass 2 uh, flowchart of the assembler. So this is the flowchart for pass 2 of the assembler, in which has to be initialized. Then we read the entries from the pass 1, in which we determine a pseudo operation, such the pseudo operation table, POT table. If operation is found, then we determine its type. After determining the type, we convert and output the constants, and then we determine the length of the data space used. We also determine the length of the type of the pseudo operation code. Then we also, after finding the type of the instruction operation code, we also indicate available base registers to be used by the program, and also indicate unavailable base registers. Whether if available or unavailable, we have to indicate the situation and the condition in the program. Then after searching for the pseudo operation code in the table, then we search the machine opcode table for machine operations defined in the program. Then we get the instruction, its length, its type, and the binary code that is used to define the instruction. Then we evaluate the operand expressions by searching for value of symbols used in the program from symbol table using the symbol table get function. After that, we assemble together all the parts of the instruction, and then we update the location counters value, and we move to the next instruction to be read from the pass 1 entries. And when we encounter the end statement, we just end is encountered. It means all the execution is completed and the complete assembly language program have been converted to the machine language code. So and is the terminating statement which terminates the uh, translation of your assembly language program into the machine language code, because complete program has been translated. Then we move to the exit. That means the process is completed. So then comes when we are translating, then there might be some errors that are reported in the program by the assembler. So these are the list of errors that are reported in pass 1 of the assembler. The first one is listing an error in first pass has the advantage that source program need not be preserved till pass 2. भी सोर्स प्रोग्राम को प्रिजर्व करने के लिए नहीं है, पास जरूरत नहीं है पास्ट टू तक. तो एट द इनिशियल स्टेज हम क्या कर लेंगे, वी विल फाइंड आउट द एरर्स. बट लिस्टिंग प्रोड्यूस्ड इन पास 1 कैन ओनली reports contain errors, not all. That means it can contain only the reports about the errors, not the actual errors that are determined. So from the below program, error is determined for example, at statement 9 and then 21. So statement 9 gives invalid opcode error because MVR does not. But also undefined symbols are identified in the error reporting of assembler. Then also the error can be, if detected early in the pass 1, so that will not be moving to the pass 2 of the assembler, and the convert the translated object code will be uh, less errors, or with no errors after the translation. So this is all about assembler and two pass assembler. We have discussed all its data structures, its flowchart, its functioning, how do you use it, and if you find any problem regarding this, you can contact me. Thank you. Thank you very much.